Okay, so the last talk is by Zihan on query complexity of metric Steiner tree.
Okay, thank you very much. Sorry for the tech failure. I also want to thank the organizer again for inviting me here. So I am Zihan Tan. I'm from Rutgers. I'm currently a postdoc at DIMAX Rutgers University, and I'm going to talk about our result on query complexity of metric Steiner tree. And this is based on joint work with Sanjeev Khanna and Yu Chen, both from Pennsylvania, University of Pennsylvania. Okay, so in sublinear graph algorithms, we are not allowed to read the whole input graph. And therefore, many classic problems, we cannot hope to obtain an approximate solution, but instead we can only get an approximation of the solution cost. For example, there is a matching problem, metric TSP problem, metric MST problem. Okay, so in this table, there are some previous work, upper and lower bounds shown in this table. By the way, here we only consider the query complexity, and we are specifically considered the pair query model, in which we are allowed to give the oracle a pair of vertices, and the oracle will return to us a distance between these two vertices. So for example, when the input is a graph, then the oracle will return to us whether or not there's an edge between them. Okay, basically 1 or 0, whether or not there's an edge. If the input is a metric, then the oracle will return to us what is the distance between these two vertices. So these are some previous results, both showing that solution finding is significantly harder than the cost estimation. So for matching problem, if we just want a constant multiplicative epsilon n additive approximation, then omega n square queries are needed. Basically, you need to query everything. Okay, and if we just want a constant approximation, or constant and epsilon n additive error approximation of the solution cost, the matching cost, matching basically the matching size, then linear in n queries are enough. Okay, and similar things happen for metric TSP and metric MST. For metric MST and TSP, if we want an approximate solution, basically a tree or a tour, then we have to basically has to query everything, omega n square. And if we want for MST, a 1 plus epsilon estimation of the cost, then just linear in n queries are sufficient. And if we want just a better than 2 approximation for TSP, because MST is always a factor 2 approximation for TSP. So better than 2 is something non-trivial. If we want something non-trivial, then just n to the 1.5 queries are sufficient in some special cases. So these are some previous work and other work. And of course, we have seen some other examples in the previous 2 days, like hierarchical clustering and Earth-bound vertices, etc. Okay. So this shows that there's a separation between solution finding and cost estimation. And of course, not all problems we can estimate its cost efficiently. For example, if we just are given a metric and we want to find the minimum distance between any pair, then we sort of have to query everything, because it can be just a closed pair hidden there. Unless you touch it, you will not find it. So this is one example. You have to query a lot. I mean, in this case, you cannot even hope for a good estimation. And also, if we want to estimate the diameter within a factor better than 2, then the same thing. Basically, it's possible that the whole metric is a uniform metric and there's just one pair with distance, either 1 or 2, you do not know. Unless you touch it, right? Until you touch it, you don't know. Okay, so basically, if you want to be able to do something in the cost estimation, the object we want to find have to also satisfy some global property, in the sense that has to contain many edges instead of just only one. Okay, so in this case, MST and TSP, they are all objects containing n edges or so. Right? So basically, the idea is if we want to estimate the cost efficiently, the object we want to find is global. And in this sense, most likely, the imposing a metric constraint will make the task easier. So in this work, we consider another problem, which is global itself, and also comes with metric input. This is the metric Steiner tree problem, also known as the Steiner tree problem. Okay, so the input is a edge-weighted graph together with a subset of vertices called terminals. Okay, and the goal is to compute a connected subgraph G with minimum total weight that spans all terminals. Okay, so it is called a Steiner tree, but its goal is to find a connected subgraph. And this is because if you want to minimize the total weights, then it has better to be a tree. Because if you have a cycle, then just deleting any edge will not destroy the connectedness of the graph, and you get a strictly better solution. So it's called Steiner tree. And it's not hard to observe that it's actually equivalent if we're, instead of giving an edge-weighted graph, we're given a metric on set of vertices, because it's just equivalent to view the input as the shortest path distance given by the given by the graph. And if you really want to select an edge that is not in the graph, it does not hurt to select the shortest path connecting these two endpoints. Okay, so it's equivalent if input is just symmetric. And it's kind of regarded as one of the most fundamental NP-hard problems, and a lot of work has been dedicated to study its polynomial time approximability. And up to date, the strongest approximation is slightly better, slightly worse than log4, achieved by several independent work. And the strongest hardest result is only ATX hard, which rules out 96/95 approximation unless p equals NT. So in this work, we consider the query complexity of both solution finding and cost estimation tasks of this problem. And together with some previous work, we sort of obtain a rather comprehensive understanding of the query complexity in all kinds of approximations. Okay, so this table, this figure basically shows our results, and the horizontal axis shows approximation ratio, the vertical shows complexity. So basically a dot here or a line here means in order to get some approximation, you need at least what number of queries, or at most what number of queries. Okay, so in this picture, the red line and red dots shows the complexity of finding a solution to some approximation. And the green lines and green dots shows the cost of the complexity of estimation, the cost. Okay, recall that we are still in the query model, so we give the oracle pair of vertices, it returns to us the distance, and this is considered as one query. Okay, so note that all lines and dots here, they are not upper or lower bounds, they are tight bounds, they are all tight bounds. So whenever there's a line segment, then it means we have shown that in order to achieve this range of approximation, we have proved both upper and lower bounds that are matching. Okay, so these are all tight bounds. So let's look at the results. So there are two phase transitions happening, and there are also some separation between the blue and the green and red ones. The first separation happening, phenomenon, like phase transition phenomena, happened at 503 approximation. Yeah.
K is the number of terminals?
Yeah, sorry, K is the number of terminals, N is the number of vertices, and in the worst case, K can be order N. Okay, so the first phase transition happened at 503 approximation. What we show is if we want a better than 503, so between 1 and 503 approximation, then even estimate the solution cost requires N squared queries. And if we just shoot for a 503 approximation, then even obtaining an approximate solution only requires NK queries. Okay, so there's a first separation at 503. A second separation happens at factor 2 approximation, and this is mainly because the MST, so terminal MST, we just focus on the terminal, like metric in use on terminals, ignore all standard vertices. Then MST on this metric will always be a factor 2 approximation for the standard tree cost. And this basically explains why like factor 2 is easy, because it somewhat reduced to the MST cost estimation. So except for this phase transition happening at 503, another very interesting regime that I consider most interesting part is a better than 2 approximation. So 2 minus epsilon 0 approximation. If we want to beat the MST estimation, then how well can we do? In this case, this is sort of the only unclear part of the picture. What we get is an upper bound and a lower bound. The upper bound is a sublinear algorithm, well, sublinear in n square algorithm. Okay, so what we get is a complexity of n to the 12/7 plus kn 6/7. So even in the worst case, when k is on, this is still below n squared. So this is why we call it a sublinear algorithm. And in the regime where k is close to n, like k is like n to the point a or more, this is even smaller than nk. So this is strictly below this line. Okay, and this is like sort of the most interesting part regime that we consider this bound to. And the lower bound, we also have a lower bound, which is n plus k to the 6/5. So in the worst case, it is indeed superlinear in n. So if we just consider in terms of n, it's less than n to the 1.9, larger than n to the 1.2. What is the right exponent? We do not know yet. So in the remainder of the talk, I'm going to present like two results if time permits. The first is the phase transition at 503, and the second is the approximation algorithm, like a query algorithm for estimating the cost to within the factor better than 2. So yeah, probably it's in the PDF mode, so the animations are gone, but yeah, I will try to do best. Actually, the 543 approximation, so in order to show the phase transition, we need to show sort of two things. when we want a 5 over 3 approximation, we only takes NK queries. And if we want better than that, it takes n square queries. So the algorithmic part actually follows from this nice structural theorem, which we proved from scratch ourselves, but later we get to know that it follows from a combination of two works, like roughly 20 years ago, 30 years ago, by Dingzhu, Du, and Zelikovsky. Okay, so this structural theorem says that there always exists a 5 over 3 approximate standard tree that uses only terminal edges and terminal standard edges. Okay, basically this structural theorem immediately applies this NK bound because we do not need to query anything about standard. We only care about terminal and terminal standard. And there are how many of them? NK total. Okay, and basically I'd like to briefly present the proof because I think it's still need very neat. Yeah. So the goal is to show that there's approximate standard tree solution, standard tree whose cost is within 5 over 3 factor from the optimal one. And the idea is to take an optimal standard tree and iteratively modify it by deleting standard edges and replace them with standard terminal edges or terminal edges, so that in the end we have no standard edges at all. And in the process, in the iterative modification process, we do not increase the cost by a factor of more than 5 over 3. This is the idea. Okay, so let's briefly illustrate the idea by some pictures. We start, let's assume for simplicity that the optimal standard tree here is just a complete binary tree. Okay, this is actually can be essentially the hardest case and captures the ideas of iterative modification. And let's say that the root, we want to start from the root. We want to immediately delete like the two standard edges incident to the root. Okay, so we want to delete these two edges, but we want to still maintaining the connectedness of the graph. So this root and together with these two instant standard edges, they serve as like connecting the left subtree to the right subtree. So if we want to delete these two incident edges, we need to replace them with some other edges that does the job. Okay, so basically the leaf will make this choice. Either it says I'm staying here. Okay, so we want to delete standard edges, but we do not necessarily want to remove all standard vertices. So the root may just want to stay here. So either it wants to stay here and tell the left children to find a terminal for him, and tell the right children to find a terminal for him too. And then these two terminals are fine. And then the root says, okay, I'm going to connect to them. So I will discard two incident standard edges and replacing them with two standard terminal edges. Okay, this is what the root will do. This is one possibility. And also it may just decides that it's going to leave, it will not going to stay. And they tell one of its children to stay and tell the other children to find a leaf. And then this leaf will directly connect to the children that decide to stay. So this is two other possibility. So either it tells left children to find a terminal and the right children to stay, or the other way around. Okay, so we just explored these possibilities. And basically this is one step of dealing with the root. And the idea is removing two edges, replacing them with either one or two edges. Okay, we need to pay the cost. I mean, when we add one more edge, we need to pay its weight. And since it is symmetric, the total weight of the new blue edges will be bounded by the tree path cost. And this is shown in a dashed line. Okay, and if this happens, we say that the corresponding tree paths are covered. Basically, in the end, we want to compute, we want to count how many edges, how many times an edge is covered. And we will be eventually showing that 5 over 3 in expectation. So this is sort of one illustration of one step. Basically, the root makes a decision and pass along some terminal finding tasks to one or two of its children and downwards. And what we really can show is that via a delicate top-down randomization process, we can ensure that every tree edge is covered in 5 over 3 times in expectation eventually. Okay, after we handle this process at all vertices. So not going to the very detail of this dedicated top-down randomization process, but the idea is for every standard vertex, either one of the 3 possibilities will happen, and they all happening with probability 1 over 3. So either it decides to stay and pass along some tasks from the root and create a pair of new tasks to these children, or it's passing along in this way, or it passes on to both of the children. And in each of these cases, the edges are covered either once or twice. And since they're happening always probability 1/3, we can ensure that eventually every edge with in expectation, it is covered 5/3 times, and end of the proof. So iterative modification until we only get terminal edges or terminal standard edges. So this is part of 5/3 upper bound algorithmic result. In order to complete the phase transition, we want to show that if we want a better than 5/3 approximation, then it requires n² queries. And this is the hard example. We start from, there's no animation here, but yeah, we consider those red circles not here for now. So we start with a complete binary tree, which just contains the brown vertices and the red vertices. Okay, we start with a complete binary tree. And in order to rule out 5/3 minus epsilon approximation, it is enough for the tree just to have a constant depth 1/epsilon. When epsilon is a constant, it's a constant depth. Okay, so the tree has constant size, a number of vertices constant size. So we then replace every brown vertices, every non-leaf vertex with a group of standard vertices. Okay, so we want to create a metric that contains n vertices in total. So we basically replace each non-leaf vertex with a group of standard vertices. How many of them? n/2 to the 1/epsilon. So that in total we have n vertices. Okay, and then we design the metric delicately. In each group, we designate one of its vertices as a special vertex, so that the brown one actually can be viewed as a special vertex. And the metric on the special vertices are just the tree metric, the tree distance, shortest path distance induced by the tree. Okay, and for all other distances, we delicately design them. So 2 + 1, 4. So it's a design in the delicate way. Basically, it is as far as that it can get without violating the metric constraint. And in the meanwhile, it does not help at all in obtaining a better than 5/3 approximation. Intuition of that is basically this is an example where the previous analysis on the previous page is tight. So randomization, when you are very symmetric, very balanced, randomization give you something tight. And this is indeed something tight. So it does not help at all in getting a 5/3 approximation. So observe that basically the special vertices, there are only constant number of them. And it can be them, there cannot be them. So they can exist or not exist. In order to tell the difference, you have to touch some special vertices, and there are only a constant number of them. So in order to tell the difference or certify their existence, n² is needed. And that completes the 5/3 phase transition. So in the remaining of the time, I will briefly illustrate how we get a better than 2 estimation in a sublinear number of queries. So since it's folklore that if we just focus on the terminal induced metric and look at the MST on them, so MST, minimum spanning tree, just on terminals, it is a 2 approximation. So the goal of getting a 2 minus epsilon 0 approximation estimation is just by either confirming that it's bounded away from MST or it's bounded away from MST over 2. And we just start from MST and see whether or not we can save some cost from them, utilizing the standard tree, utilizing the standard vertices. Okay, so in a special case where it's 1-2 metric, we can further assume that the distance between terminals 2, distance between standards 2, distance between a standard and a terminal can be either 1 or 2, where 1 is shown in blue. Okay, in this case, that's a very special case, illustrates the idea. So if the terminal metric is a uniform 2 metric, then any tree is a spanning tree, a minimum spanning tree, and this is showing green. So what we can do by utilizing the standard nodes to save some cost is, for example, we just take this vertex and replace these 2 green edges with these 3 blue edges. We add a cost of 3 and removing a cost of 4, thereby saving a cost of 1 without destroying the connectedness of the graph. Okay, so this is how we utilize the standard node to save some cost from MST. And if we take it back and see what we are really doing, it is actually solving a coverage problem, where the underlying ground set is a set of all terminals, and every standard node corresponds to a subset of the ground set, where every, this standard node is just corresponding to these 3 terminals, where it has weight 1 connections to. Okay, so actually what we are solving, the best way of getting the saving like this is finding a collection of sets, and the saving is cover of these sets minus coverage of these sets minus the number of sets. So in this example, if we select these 3 sets, then the number of sets we're selecting is 3, and the coverage we get is 7. The saving we get is 7 minus 3 is 4. So this is like what is the best we can do in this method is like really this coverage solving problem. And equivalently, this can be viewed as a set of actually a variant of set cover problem. Only we are not minimizing the set cover size. What we are computing is the set cover size deficiency. It is k minus set cover size. So as long as we can cover something non-trivial, we can find some saving. And this is really k minus k cover size. And one technical contribution of our paper is that we do have an n to the 1.5 query algorithm for getting a constant approximation for z value. Basically the saving we can get at best from this approach. Okay. So this is a special case, but they illustrate all the main ideas. I'm probably going to skip a few lines, but the idea is we just discretize the edge weights. In the beginning, we compute a hierarchical structure of terminal MST, and we see how they're connected by rounding the weights to 1 plus epsilon to some integral component, integral exponent. So all edges are rounded either up or down, and they are all 1 plus epsilon to 1 or 2 or 3. And we find savings layer by layer. Okay. Only a slightly different is when we go levels up. For example, these green edges are already added. The ground set changes a little. It's just the green components instead of the terminals alone. Okay. This is slightly like a technicality, but the idea is just to discretize the weights and find savings layer by layer. In the end, we aggregate all the savings. If we sum up to some constant fraction of MST, we claim the total standard tree cost is bounded away from MST. And this is indeed correct because we can just use the corresponding standard nodes to save some cost. We can indeed construct such a standard tree. And if the total saving is negligible fraction of MST, then we claim lower bounds. So this is the whole algorithm. Maybe there's some proof needed for like why is that the last bit true. So in the case where we haven't found any saving, it is indeed bounded away from MS2. I'm probably going to ignore that part proof. It's still by some iterative modification like the 543 proof, but yeah, with actually a reverse direction. So in the end, a last comment about complexity. We have a n to the 1.5 query algorithm for finding the saving. There's just a log n level saving. So total query complexity will be n to the 1.5 poly log n like that. But this is based on computing a hierarchical structure of MST first, which requires k squared. And so basically, initially, we get a complexity n to the 1.5 plus k squared. But in the worst case, k can be n, so this is n squared, and it's not very good. But luckily, the saving finding algorithm, n to the 1.5 algorithm, is also local. So it does not need to know the hierarchical structure in the first place, like all the structure. But whenever it just wants some information from it, it does local exploration at that time as needed. So we managed to eventually get a balance between these two complexity, and the balance point is n to the 12 over 7 plus k n to the 6 over 7. This is the eventual bound we get. So the idea is discretize, use a set cover subroutine, and eventually balance this like two complexity. This is another technical part, not going into. And yeah, can ignore this last bit of proof of the correctness. So just a summary and some future directions. In this work, we consider the query complexity of standard tree cost estimation, and we have a sort of comprehensive understanding of all kinds of approximations. The open problem, I think the most interesting one is what is the real answer for better than 2 approximation, like slightly better than 2. And some note is improving the query complexity of this set cover variant will indirectly yield a better bounds for our whole goal. Okay, that's all I'm going to say today. Thank you very much for staying strong until the last talk of the workshop.
Do you think there's any like natural scenario where little O of n algorithms are possible?
Little
like,
n?
Little O of n, like under some constraint, either on the graph or
so we do have a lower bound n here, little of n. So if you want a better than 2, it's not possible. We do have an n here as lower bound.
But is there any sort of, I don't know, it's more speculative. Is there any situation under which we could hope for little O of n algorithms, like either
so the phase
graph
transition
or maybe a different approximation? Or?
Okay, yeah, so the phase transition is sort of interesting. So when you shoot for a better than 2 approximation, n is irrelevant. It's just k, like k squared or k in like either finding the solution or estimation cost. Yeah, so if you think of k as small, like k squared smaller enough than n, then n is irrelevant. like phase transition at 2, basically, I think is the point you're asking. How thing reduces to MST estimation now.
Hi, yeah, nice talk. So connecting to Rajesh's talk yesterday, if the points are in RD and you want a better than 2 approximation, is there anything known?
Yeah, that's a nice question. We haven't thought about it. We just thought about the general metric. I suppose this lower bound example will probably break down. Maybe it's not good for RD. So yeah, maybe the better ratio can be achieved. But yeah, we haven't thought about it.
Thanks.
Current example does not work.
Any other question? Okay, so let's thank Zihan and all the speakers and participants.